All right, I wanted to make a video to go over some problems on practice 1.3a number 4 based on relative velocity. So we've been talking about vectors, and we can use vectors like displacement vectors. We can say that if we have some object that starts at a point here, let's say, and then it moves in some path, but it ends up at a point here, it is displaced a vector quantity from its origin, from its starting spot, and we can represent that vector this way. And we can say that this is the displacement. And this vector quantity has two parts to it. One is its magnitude, maybe the number of centimeters that this object has moved away from the origin. And the other is an angle. So this vector has not only how long it is, but it also has a direction. It's like it has moved this many centimeters at this direction, so that you could determine from the origin, if you knew this displacement vector, exactly where this object had ended up. All right, so we can use vectors to talk about displacements, but in practice 1.3a, we're using vectors to talk about velocities. All right, so let's jump in here. Problem 1 says a car A moves to the left with a speed of what should be 40 kilometers per hour. So I'm just going to represent that. This is like A, it's to the left. It's 40 kilometers per hour. And this is the velocity of car A, right? So no longer are we using a vector to say that car A has moved this far, let's say, but rather this is the velocity. It talks about how fast car A is moving. So the magnitude of a velocity vector represents the speed. Like, you know, if the car was looking at its speedometer, the speedometer might read 40 kilometers per hour, and the car might be heading to the left. All right. Another car B moves to, well, let's pick a different color, moves to the right with a speed of 60 kilometers per hour. So I'll draw B here. It moves to the right faster, so I'll make that a little longer. This is the velocity of car B, and it is going 60 kilometers per hour to the right, let's say. All right, the problem asks us to find the relative velocity of B with respect to A. The way we write that is we say the velocity of B with respect to A, and there's a formula that says that all we have to do is take the velocity of B, take out of it the velocity of A, and we'll have that difference represents the relative velocity. All right, so velocity B with respect to A is equal to velocity B minus, I could write minus, but I'm going to write plus a negative velocity A. All right. And this is not just any ordinary addition subtraction, this is vector addition, so we need to use vector addition in order to solve this. All right, so we're going to start at some origin point. We're going to define our origin point as just any point, and we're going to draw first vector B. So I'm going to draw vector B here. I could just drag it down here, but I don't have that technology with my Crayolas here. So I'm going to redraw it. This is vector B, and it's equal to 60 kilometers per hour. Plus, so I'm going to add the other vector, its tail here, plus a negative vector A. So vector A is going to the left. A negative vector A is going to be the same magnitude to the right. I'll draw that here next. Negative vector A right, and our resultant after we do a vector addition just is a vector from the origin to the head of the last vector. I don't know if you can see this red vector here. That's what the resultant is, and that resultant is equal to VBA. And as you can see, it's going to have a magnitude of 100 kilometers per hour. All right. to the right, to the right. Next up, boat A heads, you know, we should make that clear. Since it is a vector quantity, we should write VBA is equal to 100 kilometers per hour. We could draw an arrow this way to make it clear that that's to the right, or we could say to the right. All right. Number 2. Boat A heads east at 7.2 meters per second. Now we have to define which way east and west. You know, it's like we think of this as going this way. You know, north is up. We think of it as going this way here. But if you ask somebody in Australia, I think that, you know, they see the whole world. You know, it's like, no, they don't. They use the same thing. All right. So we're going to use this kind of convention for our directions here. So if boat A heads east at 7.2 meters per second, then I could draw boat A as going this direction, 7.2. So we'll call this the velocity of A. It's equal to 7.2 meters per second. Boat B heads north at 5.8 meters per second. So let's draw boat B. It's headed north, not as much magnitude here. So this is the velocity of B. It's equal to 5.8 meters per second. The problem points out that both of these are measured by an observer that is fixed in one location. You know, this idea that like there is no such thing as a non-relative velocity. Every velocity is relative. If there isn't what do you want to call that? If there isn't a reference frame that is given to you, then we assume that it's Earth is the reference frame. But the truth is that, you know, what kind of a reference frame is Earth as being still, or the zero velocity reference frame, as we are moving through space so quickly, you know, not only spinning around our sun or around our own axes, but also, you know, spinning around the center of our galaxy. And, right. So we have this thing in physics where every velocity is relative. There's nothing that's still, right? So it's all just relative to others. All right. It says determine the following. For part A, find the velocity of boat B relative to boat A. So they're saying find velocity of boat B relative to boat A, and we know that that's the velocity of B plus the negative velocity of A. No problem. Here's how we do this. We say, we'll pick, this is vector addition, right? We'll pick a reference frame here, or an origin, I guess. We'll first put vector B on it. That's going up at 5.8 meters per second. Then we'll put a negative vector velocity A. So instead of this way, it's going to be going the opposite, 7.2 meters per second. You can see that I've very carefully drawn this to be exactly a right angle here. All right, and what we need to find is the vector sum of those two vectors. So it's going to be, the resultant is going to be a vector that is the hypotenuse of this right triangle. And this is going to be VBA. Well, how do we find the length of VBA? Well, no problem. VBA is well, we could use Pythagorean theorem, right? If we kind of, for a moment, call this like A and B and C, we could say that C is equal to the square root of A squared plus B squared. And so then we can say, all right, well, VBA, that's really side C here, is equal to the square root of this squared, so 7.2 squared, plus 5.8 squared. And if your calculator is working right, I think you get 9.2 meters per second. But this is only the magnitude of our vector, right? This only says what is the magnitude of that vector. in order to answer a vector problem, we have to give both a magnitude and a direction. So really we should find, what is this angle theta here? We should say it's 9.2 at some angle theta. And in order to solve that problem, all right, let's divide out a little space for us here. Find theta. In order to solve that problem, we're going to use this idea that toa is the tangent of theta is equal to the opposite side, which in our case is 7.2, over the adjacent, which in our case is 5.8. There's all kinds of videos out there if you're curious how to use SOHCAHTOA and how to identify which side is which, on Khan Academy or whatever. So I'll assume that you either have that or you know where to go to figure out how to use SOHCAHTOA correctly. So the tangent of theta is equal to 7.2 over 5.8. And to solve this, all we have to do is take the opposite tangent of both sides. Take inverse tangent of this side and inverse tangent of this side, and we get that theta, if our calculator is in degrees mode, is equal to 51 degrees. All right, so there's a couple ways we can represent this answer. For our answer, we can say, let's write our answer here. For our answer, we can say that VBA is equal to 9.2 meters per second at 51 degrees. Now this angle, 51 degrees, is starting from north. We're going to head in the west direction, right? Starting from straight north, we're going to point towards the west, 51 degrees. So we would call that west of north. Or likewise, you could kind of see the world this way. You could say, well, I could picture this angle here as the complementary angle, which would be under the 39 degrees. So I could say that VBA, or VBA is equal to 9.2 meters per second at 39 degrees north of west, right? That is, if you're pointed straight west and you go 39 degrees north of that, towards the north, then if this angle is 39, we still have the same direction here. All right. Next up, it says find the velocity of boat A relative to boat B. So let's take a look at that one. You know what? I'm going to let you take a look at that one, but I'll tell you what you should get. So if boat A is heading towards boat B, velocity of boat A, if boat A is heading towards boat B, and boat A sees boat B as going 9.2 meters per second, then it's going to be the same both ways, right? So you're going to get, again, 9.2 meters per second, but the direction is going to be all wanky, right? So it's going to have different direction. So for part B, I get 9.2 meters per second at either 39 degrees south of east or 51 degrees east of south. All right, and let's take a look at this last problem. All right. Rain comes vertically down at 8 meters per second during a rainstorm. So this rain is traveling vertically down. We could just write 8 meters per second here. And a girl runs towards the right with a velocity of 11.3. Again, measured by a person fixed on Earth. Find the velocity of the rain relative to the running girl. So you ask the girl which way the rain is going. What does she think? All right. Draw a picture to clarify the direction of the relative velocity vector. All right, let's get into it. So we want the velocity of the rain relative to the running girl. So we're going to say the velocity of the rain relative, I'll just put a slash in here to keep it, of the girl And that's just going to equal the velocity of the rain minus or plus a negative velocity of the girl. So let's draw a picture. All right, we have our rain velocity is headed off in this direction. And then we have to add to it a negative velocity of the girl. So instead of 11.3 to the right, we're going to go 11.3 to the left. This is negative velocity of the girl. And our resultant vector is going to be this vector here. So you see the girl thinks the rain is kind of heading at her a little bit. It's hitting her in the face. And so we would find this is the relative velocity that we're looking for. We need to find both its magnitude and its direction. For the magnitude, well, we're just going to say that the magnitude is equal to the square root of a and b squared, right? A squared and plus 11.3 squared. And for the magnitude, then we're going to get 13.84. We round it to two significant figures. That's what they give us. And I get 14 meters per second. All right, so this is 14 meters per second. And now we need an angle. So how do we represent the angle here? I think it's good to say, we'll just draw an angle here and say, let's find that angle. And then we'll draw a picture with our answer that shows that that's the angle that we're really talking about. All right, so if this is our angle, then we know that this is the opposite side, OPP, and this is the adjacent. And we know that the tangent of our angle theta, so tangent of theta, has to equal the opposite over the adjacent, right? Because TOA is true. Tangent is opposite over adjacent. So the opposite in this case is 11.3 meters per second. The adjacent is 8 meters per second. We need to take the inverse tangent of both sides. So it's going to end up that the inverse tangent of 11.3 over 8 gives us 54.7 degrees. And we're talking 2 sig figs, so let's talk 55 degrees. All right, so here is our magnitude. Here is our angle. And I think it makes sense to represent this with something like this, that the velocity of the rain relative to the girl is equal to 14 meters per second at an angle of 55 degrees, but we're talking about this angle here. So I'm going to draw a dotted line, I'm going to draw a vector, and I'm going to make clear that this is the angle that I want right here, 55 degrees. All right, that'll do it.